Very pleased to have our first speaker, Giulio Tiozzo from University of Toronto, who will tell us about how to count loxodromics for group actions.
Thank you. So, thanks very much for letting me open this conference, which looks pretty nice, at least in paper, we'll see. And yeah, unfortunately I brought some bad Canadian weather from Toronto, so unfortunately for you guys. But anyways, this is supposed to be a computational conference, so disclaimer, this talk is not really that computational, even though I'm interested in computational issues, and that's why I put this teaser at the beginning. In fact, this is a picture which we produced actually with Nathan a couple of years ago at ISERM. And I'm going to be talking a little bit about random walks in the mapping class group, and this is a picture that you would get if you compute eigenvalues. So you take a random walk in the mapping class group, you look at train track representative, and you look at all the possible eigenvalues. And
is that the unit circle?
And right, that's the unit circle. And another interesting story is that you should be aware of computational methods, because it seems like in this picture there's all these roots in the unit circle, and there's most definitely are. But on the other hand, you can prove that there shouldn't be. I mean, on average there shouldn't be any. So, and in fact, it turns out that eventually I convinced Nathan to push the simulations, and eventually if you do a very, very long simulation, you see fewer and fewer of them. So these eigenvalues on the unit circles are actually interesting, but you should be careful about this. Anyways, what I'm really going to be talking about is not so much finding results about counting, but proving that things you might verify by doing say numerical simulations is actually true. So for instance, the loxodromic elements will be generic. And so this is it's work mostly with Gekhtman and S, and I will first introduce a little bit of the setup and also the comparison with the random walk case, which many people have studied before, and then I will talk a little bit about applications. And my main applications in this talk will be relatively hyperbolic groups and right-angle Artin groups. And hopefully I will focus a little bit on right-angle Artin groups, because everything becomes very explicitly computable, so you can write down explicitly the graphs in question. So I will maybe try a little bit of that. Okay, so anyways, let me start. So what's counting? Well, you have a finitely generated group, and you have a finite set of generators, and you can construct, you have a word metric, so the set of elements which can be represented by words of length at most n, and this is sphere, and then you can count. So you have a subset of the group, and you can count how many of these elements have length exactly n, and you divide by the cardinality of the sphere. So that's kind of the most natural way of counting. And this defines what we call a counting measure of the group. So for each n, you take this sphere or ball. You can do either. Usually ball is more stable, but actually everything I'm going to be talking about also holds for spheres. So I'll just keep with that, which is kind of stronger. But still, you could do that for balls or spheres. And then you want to say a set is generic if, well, basically with overwhelming probability. So for instance, with probability which tends to 1, this number of elements, these elements have the property that you want. So this is some notion, and the great motivating question for this story is this question, which is very old, and I can never trace exactly who posed it. I conjecture it's a conjecture of Thurston, but I haven't verified this conjecture. Is that in a mapping class group, if you take generated sets and you count pseudo-nosovs, so they should have full density, they should be generic. And crazily enough, this conjecture, even though it's one of the starting ones, it's still open, and I'm not going to prove it, so don't get too excited. But in fact, there has been recently some interesting work, which is kind of not too related to the methods I'm going to be talking about today, but for instance, this short paper by Complete and Wist in 2017, which says that the positive proportion are pseudo-Nosov. And possibly there was also some other argument before, so it's not clear. But anyways, there's some not so complicated argument for getting positive proportion, but still no one can get full proportion. So in general, what is this type of setup? But you can do something else. Instead of doing counting with respect to balls, you can count with respect to random walk. So the picture is you have space, and you start with a point, and then what you do? Well, I think G is a group of isometries of, so G acts on X by isometries. This is X. And then we pick a measure mu on the group. So of course everybody prefers to think of it in terms of, say you have finitely many generators, you pick each of them with uniform distribution, but you could do more complicated things. Anyways, what you do is you pick one element, G1, according to this measure, randomly, and you pick G2 and G3 and so forth, and you construct this sequence. And then basically you take the product of those, so now you get a sequence of elements which is no longer independent, and you ask what happens. So this is your random model. And the question is what happens with high probability to this element. And the famous theorem proven independently with different methods by just Mar and Igor Rive is that if you take such random walk on the mapping class group and you look at pseudo-Nosov elements, the probability that it's pseudo-Nosov tends to 1. That's it. So this is a very nice result, and we're going to see that we can generalize this to various setups, but it still doesn't solve the original conjecture, because this distribution that you get by taking random elements is a priori completely different from the distribution you will get by taking uniform measures on balls. Right, and in fact, well, from a computational point of view, of course, we kind of like random walks because they're easy to simulate. So you can produce lots and lots of fixtures with this method, while simulating balls is very hard, especially for the mapping class group, in fact. This is a real problem that you don't really have a good way of producing exact geodesics in the mapping class group. You can produce quasi-geodesics fairly easily, but geodesics on the nose, they're much harder. And in fact, everything I'm going to be talking about will strongly depend on the generating set. So in a sense, it's not going to be quasi-isometric invariant, because if you have two metrics which are quasi-isometric on the same group, well, and this group has exponential growth, if you do counting with respect to one set of balls or counting with respect to the other set of balls, it's very different, because this multiplicative error in the length gives an exponential difference in counting. So in a sense, this is not really geometrical theory. This is not quasi-isometric invariant. Everything will depend very, very strongly on the generating set.
Are the two distributions the same for a free group with a basis?
Right, so the toy example where we know, and this is the thing, so I will talk a little bit more about this, but yes, for the free group, with this simple random walk on the free group, then yes, we do know that the counting measure and the random walk measures are indeed asymptotically the same. But this is pretty much the only case. Any other questions before I keep going?
So wait, could you say the thing that is the same again?
Oh, in a free group with a simp, if you can do counting with respect to balls or spheres and the usual word metric, or you can do simple random walk. And then the distribution you get from these two processes asymptotically when n is large, they are the same. In fact, they induce the same measure on the boundary. Maybe in the next slide I will make it more precise, but I skipped the. So in particular, yeah, the general setup is that you can do, if you do random walk, say, like on a space like this, you can have a hidden measure on the boundary. So you can say I have a subset of the boundary, let's say A, and I say what's the probability that I'm going to hit A. But this is some notion of measure which kind of comes from the limit of doing this random walk. And this is one measure you can put on the boundary, but it's not the only measure. And in fact, the other measure is kind of, it's not really Patterson-Sullivan, but let's say Patterson-Sullivan type measure, which is I pick a ball or a sphere in the group, and I pick uniform measure. Say here, I pick uniform measure on this ball, and then I take the limit as n goes to infinity. And in many cases, this group maybe has a nice compactification or nice boundary at infinity, so then this measure becomes a measure on this boundary at infinity.
There's no Poincare series here.
Right, that's why I said it's Patterson management type. In fact, for instance, when everything works, so it doesn't matter if you weight it or not. In most cases, but the classical one, of course, for primary groups would be to weight exponentially over the ball, so that's kind of more regular. But for instance, for hyperbolic groups, you get at least a measure class just doing this thing. So yeah, you could weight it slightly differently, but basically it's the same measure class. Okay, and yeah, so in fact, there's a huge literature about this kind of questions, which I'm going to just say as a motivation that when you have these two processes, you can ask whether these two measures are the same or in the same measure class. And in particular, you have this kind of Patterson-Sullivan measure, this geometric measure, and you want to know whether this can be ever produced by a random process, by a random walk. And in fact, this is really the beginning of a huge story which comes from Furstenberg, who basically did it for lattices in Lie groups. And this is the first ingredient if you study rigidity, superrigidity, this kind of questions. For instance, he proved that if you have a lattice in a Lie group, then you can produce some complicated random walk, which produces this kind of geometric measure on the boundary. But this random walk is going to be kind of complicated, but you can. And there's also many results which are negative. You cannot, these two measures are singular in many cases. And I worked a little bit on that also at some point, but there's huge literature. And for instance, for hyperbolic groups, there's also a very important result by Conan and Muchnik, which says you can realize, again, this Patterson-Sullivan measure as a Hilton measure of some random walk on the groups. So somehow, but already if you leave the hyperbolic group case, things get much, much more complicated. Already this proof is really very technical. So this is the general setup, but okay, for free group, you don't need to resort to Conan and Muchnik. You can work out the measure, and it works. But that's kind of very, very particular. Any more questions?
Wait, so you said the reason why we like random walks is because they're easy to simulate.
That's one reason, yeah.
But Furstenberg's measure, which gives you Patterson-Sullivan, it's not easy.
That's
to
right.
simulate.
In fact,
I mean, it's like you have a random walk, but it's impossible to.
That's exactly right. In fact, Furstenberg's reason is a different reason, actually. It's because it has nice, for instance, it has nice equivariant properties. If you have morphisms of groups, you get morphisms of measures, you get boundary maps, so the story is much richer. So Furstenberg's point of view was not, he was not interested in simulations, but you get these nice boundary maps. And for instance, you can prove using these random walk techniques that if you have a lattice in a rank 1 Lie group and in a higher rank Lie group, they're not commented. I mean, you cannot map one into the other. So you get this kind of results. Anyways, so let's keep going. So now, in general, we have a setup. So I'm really not talking too much about mapping class groups, but I will be talking about more generally isometry groups of delta-hyperbolic spaces. So everybody knows, I hope, what a delta-hyperbolic space. If you don't, let me just give this picture. Then you can ask your neighbor what this picture represents geodesic triangles in delta-hyperbolic groups. They're thin in delta-hyperbolic spaces. And in particular, we are really interested in groups which act on delta-hyperbolic spaces which are not necessarily, for instance, locally compact. Proper just means that the closed balls are compact, so it's kind of the same. And the reason is because, well, this is where the technical issues arise, but somehow unexpectedly and very fortunately for us, a lot of people in geometric group theory have studied such actions. So an example of such space could be if you take a locally infinite, say for instance a locally infinite tree, so a tree where every vertex has infinite valence. That's impossible to draw, but keep going like this forever. This would be such a space, and for instance, examples of hyperbolic complexes which are not locally compact. So the main first which comes to mind is the cut complex, in which the mapping class group acts. But then, for instance, for relatively hyperbolic groups, you have the Kondov space. For right-angle Artin groups, you have another construction, which is the extension graph by Kim-Kuberta. For out-of-fan, you have various complexes like this, which, for instance, the three-factor complex of the Frisch-Wixon complex. So anyways, there's a whole literature and principle which says that G maybe is not a hyperbolic group, but it still acts on some hyperbolic space, but this space cannot be proper. For instance, it cannot act co-compactly on a hyperbolic space, otherwise the group would be already hyperbolic. So that's where all these cases come from. In fact, I'm not really interested in any particular such case, but we're just going to build a general theory of isometries of delta hyperbolic spaces, but it can be applied in various situations. So in particular, what are interesting properties that we look at? Well, if you have a hyperbolic space and you look at isometry, you still have a good old classification. You have elliptic elements, which have bounded orbit. You have parabolic elements, which fix one point on the boundary. So parabolic is more complicated in a non-proper case, but you still have this trichotomy. And then you have hyperbolic elements, or if you're fancy, you like Greek words, you can call it loxodromics. And so a loxodromic element is an element which has two fixed points on the boundary, and it has this north-south dynamic. So basically, you have a repelling fixed point and a attracting fixed point, and basically the group element translates along the geodesic. Maybe there's not really geodesic because it's a space, maybe it's a coarse space, but still it has this general type of dynamics. And in fact, one way you can measure whether an element is loxodromic, you look at its translation length. So you pick basically, you want to know what is this translation, so basically you pick a point x, which need not be on the geodesic, and you consider g of x, d2 of x, and so forth, and you measure how fast this sequence grows. So this is a property of an isometry, and if it's positive, basically you get the loxodromic. So this is the same as in a usual hyperbolic space, except you cannot tell, for instance, by looking at the trace. If you have a SO2Z, you can tell by looking at the trace whether it's elliptic, parabolic, or loxodromic. In general, you can't. But this idea that, for instance, you can look at the trace should tell you that, in general, generically, elements should be more likely to be loxodromic than either elliptic or parabolic. Because elliptic would be, well, for instance, in SO2Z, you have only finally many classes of elliptic elements. Parabolic, you would have the trace to be 2 in absolute volume, so this would tell you it's a subvariety, and everything else is loxodromic, so this is kind of much more common, at least in 2-2. So that's what we're trying to prove. Any questions about this slide? Okay, so, and in fact, in general, so first of all, in earlier results with Joseph Meyer, we tried to extend this setup for random walks already to the most general setup. There have been intermediate results by some other people, but so somehow what we came up with is this most general notion that if you have a probability measure on a group of isometries, you call it non-elementary if the support of mu basically contains two independent loxodromic elements. So basically, in the picture, you would have a loxodromic element with two fixed points like this and two other fixed points which are like this. They would be completely disjoint. So you have a picture like this. And that's the only condition you need to have a genericity of loxodromics. So basically, now mu can be super strange, complicated measure with super fat tail. We don't care, but what we care about is that it contains at least these two non-elementary elements. And once you have this, you take this distribution of this random walk and you count with respect to probability, and you can prove that the probability that such an element acts loxodromically on the space goes to 1. So this is a generalization of the theorem I said before by Meyer and Riven, and it holds, and there's no moment condition, basically. That's quite important for various applications. And in fact, the zeroth application is that the reason why we care about loxodromics in the first place is because, well, if you look at X, the curve complex, acting loxodromically in the curve complex is equivalent to being pseudonosive. So we care about the mapping plus group, we care about pseudonosive elements, I hope. Otherwise, this is a wrong conference. And then on the right-hand side, so the thing is, all the philosophy here is that we really don't care at all about the analytic structure of titular space or anything like that. All these theorems can be proven, or some cases have been proven by looking at the action of the titular space and stuff. But here we only look at the purely kind of geometric group theoretic case, in the sense that you just look at coarse geometry, you look at actions on this complicated hyperbolic spaces, but still everything is kind of combinatorial. It's coarse geometric. Okay.
Giulio? Yes, just one question. The support of mu is assumed to be finite in your...
No.
Oh, okay. Any...
That's right. In fact, yeah, this is analog to a famous theorem of Furstenberg for, say, SL2R, for instance. So already in that theorem, you have exactly the same hypothesis. And the technicality here, which I will talk about probably never, but if I have time at the very end, is that the boundary of X, since X is not locally compact, the boundary of X is not compact, as in the sense of hyperbolic spaces. The boundary is not compact. So then you have to introduce another compactification. And that's the technical problem. And once you have that, you can sort of use a similar proof as Furstenberg's.
Maybe I can ask a stupid question.
Sure.
Is mu, what's the definition of support? Is it just like the...
Well, support is just a set of elements which have positive measure.
So everything is atomic.
That's right, it's a count. Oh yeah, I didn't mention that G is a countable group. Yeah, every group is countable from each other.
Good.
Yeah, so this is, I thought in this workshop everybody just was working on countable groups, but
Measures,
yeah, you don't know. Yeah, of course there's a huge literature of measures on Lie groups, and then you have a support becomes more complicated to define. But for me, everything is countable. But actually, some people, I think, worked out recently our proof. They say that our proof also works for Lie groups, but they haven't checked. But some people were interested in this case. Anyways, so this is kind of the old results, but kind of a good starting point. And now, when I started talking with Ilya and Sam, we wanted to say whether we can say something about the counting model, not the random walk model. And in fact, there's an interesting point that for counting, the exact statement as before is actually false. For kind of not so smart reasons, but you can have this example. You take a direct product of free group of 2 generators and 3 generators, and you make it act on the free group of 2 generators, that's a Cayley graph, and F3 acts trivially. And now, how many loxodromics there are? Well, if you're really, really bored, you can work it out. It's doable. And basically, you have to count how many elements are in F3, basically. So of course, these are, since F3 has larger growth than F2, basically the growth of G is the same as the growth of F3. So you have a positive proportion of elements which is not loxodromic. And if I tried to do this computation, and my co-authors tried to do these computations, and I did it again, and eventually we agreed it's 2/3, but you can challenge this. I will not be too desperate, but it's a good challenge. Yeah. So anyways, and this is kind of nice. It's a really nice group anyways, and in fact, it's a right-angle Artin group. Keep it in mind. But still you have a counterexample, and everything is nice. You will have a nice geodesic automatic structure for this group. But still, this fact that this F3 acts trivially kills all the argument. So this theorem cannot be true in complete generality. You need some condition which says that somehow this dynamics kind of mixes somehow. There's some sort of ergodicity condition.
Is there an example with a faithful action?
Well, you can actually make it faithful because I think you can say, okay, F3 acts by location. I believe you can. Yeah. You do something kind of not very dramatic in this F3 factor. Yes. Okay, so, but what is true? Okay, so this theorem comes in 2 parts, and in fact the first thing we could prove was for hyperbolic groups. So G is hyperbolic to begin with, and S is any generating set. And now you look at action, which is non-elementary actions of G on a separable hyperbolic space. So again, and now for any generating set, if G is hyperbolic to begin with, we could prove that you have genericity and loxodromics for the counting model. And so, for instance, this would be one statement. You can count elements of norm n and count how many are loxodromic on x, and this would be full proportion. And this, of course, and x, the action on x doesn't have anything to do with G in a way. I mean, x could be a very bad action. But still, we need, in this first theorem, we do need hyperbolicity. So in a way, this is not so satisfying because, of course, the part of the point of considering these crazy actions is because G is not hyperbolic to begin with. Otherwise, it's a bit less. However, there are cool applications of this little theorem, which I like this little corollary, which is a completely crazy way to prove that filling curves are generic with phi 1 on the surface. And let me write down the proof. So basically, this is the proof. So you all know the Berman exact sequence. So you know in particular that phi 1 of S could be embedded in some certain mapping class group. And this is a hyperbolic group. It's a hyperbolic subgroup of a mapping class group. And this map, which maps the surface group into the mapping class group, is called point pushing map. Basically, you push points along this curve and create a kind of sort of Dane twist. And what's interesting is that it's known, it's a famous theorem that point pushing, so let's say that P of gamma is Pseudo-Nosov if and only if, right, so if and only if gamma is filling. It's kind of amusing. I mean, I'm sure you should be able to prove it somehow other type way. But anyways, it's kind of amusing that you can use this embedding. The point is there are indeed interesting subgroups of the mapping class group which are ready to hyperbolic to begin with, and for those you can apply this theorem and you can possibly get some stuff.
So in this case, the action is on the curve complex.
That's right, that's right. So the action here is the action of the curve complex. So if it's Pseudo-Nosov here, it means, basically that P, I don't know what, P gamma star, I don't know, is loxodromic on the mapping class group. Sorry. That's right.
Wait, so in your theorem, it's
Like curve
G is
complex
also
of SP.
Right, yeah, I think it doesn't matter. It's Pseudo also. It fixes P, but it's Pseudo also.
No.
What?
No, it's isotopology identity. You need P.
You need P, right?
Yeah. So CSP.
CSP.
Okay.
Good. Okay, anyways.
It's the action of pi1, not the action of mod. Right? Because
The action of pi1 gets not to.
yeah.
Yeah, it's a sub. This you see this as a subgroup of this group. Yeah. Okay, so now how about non-hyperbolic cases? Because hyperbolic groups are trivial for some people. I don't know. I think they're not, but somehow at this point everybody thinks we know everything about hyperbolic groups. So can we extend this to non-hyperbolic cases? And in fact. So we have a general theorem, which I will talk about, and then I'm going to focus mostly on these two cases, so relatively hyperbolic groups and right-angle Artin groups. So, in fact, we still need something which reminds us of random walks. So we need some graph to count in. So in fact, we to avoid the word automatic group, because there's too many definitions of automatic group, we'll call them graph structure. So I have a group of isometries of a delta-hyperbolic metric space. Again, not necessarily locally compact. Why did they say locally connect? Certainly, yes, it's not, but it doesn't have anything to do with this. The graph structure would be just a finite directed graph, and the edges of the graph are labeled by elements of the group. And there is some initial vertex. So probably if you thought at all at automatic groups or things like this, you have seen that, say for the free group, there's a nice way to code geodesics in the free group, which basically you have the starting graph, starting vertex, and then you have a graph like this. So if you start from the starting vertex, you read A, you go to A. If you read B, you go to B. If you read B inverse, you go to B inverse. You go to A inverse, you go to B inverse. And then you can parameterize the set of reduced words by a graph. So here, if you have A, you can read A again, or you can read B, or you can read B inverse. But you cannot read A inverse, otherwise this is not a geodesic. And you keep going like this, right? So if you read from B, you can read B, you can read A inverse, you can read A, and so forth. So this will be some example.
So this is sort of saying that geodesics are easy to generate in some groups.
That's right. So
maybe not the mapping class group. But
that's right. That's right. That's right. So we will need some condition like this. And well, in fact, our theorems are more general in the sense that you could have a graph like this, which does not necessarily parameterize geodesic,
okay.
and you can still do counting, but not, I mean, counting might mean something else. So for instance, for the mapping class group, you could use, say, Moshe's automatic structures, and you can get some result, but this is not so interesting because it doesn't tell you anything about geodesics in there.
But you require that the graph recognizes every element of the group.
Well, it depends. So yeah, you need some more conditions. Let me, yes?
Is mod SP the ones that fix P?
Yeah.
How do you subject that into mod S? Sorry. Is this supposed to be a short exec sequence? Or?
Yeah. Well, you just forget what it does to P.
Okay, thanks.
That's it, right? I mean,
Every homomorphism has a representative that fixes P. Up to us.
Okay.
okay, anyways, yeah. So we could do counting. So omega 0 would be the space of paths from V0 of finite length. And you can do counting with respect to this. So there's obviously notion of length in this graph. And you can do counting with respect to this graph. And well, what the case where we like the most, but well, our theorem is a bit more general, but is that when you have, as you said, geodesic mathematic group means that every group element is represented by some path in the group in a unique way. So this would be the best possible case, but Of course, this is not going to be true in all cases, in most cases. So this would be the best case. But in any case, you could do counting. And another condition we need for graph structure is that kind of has pure exponential growth in the sense that if you count the number of paths of length n, this is basically lambda to the n up to a multiplicative constant. When lambda is positive, bigger than 1, so we only care about group exponents. So anyways, these are some ways. Now the point is that even if you have all this nice hypothesis, exactly for what I told you before about this case of F2 direct product with F3, you're still not going to have genericity of loxodromics. So you still need some more condition, which is kind of some dynamical condition, some ergodicity condition. And so in fact, there's many conditions you can apply to here. So here's one, which maybe is slightly complicated to tell, but it's kind of nice because it's a bit more dynamical, which I will call growth quasi-tightness, even though it may be confusing because it's not exactly what people say, but growth tight. It comes from the growth tight languages, but it's in some sense. Okay, anyways, what we could say? We could say that a path almost contains the word W. So let me draw a picture. Basically, you have a path gamma, which is a path, say, from the identity element in this K graph of this group, which maybe is generated by some graph structure like this. And they say that it almost contains a group element, W, if basically W kind of fellow travels gamma in the group. So here's the picture. So basically you have an element G here, and you have GW. So W is like this. And you have finite distance between these 2 points. So in particular, what you could say is that gamma contains a subpath, gamma prime, such that when you look at it in the group, not in the graph, it's complicated because you're picking representatives for geodesics. So you could have more complicated things. But it's enough to say that in the group, this representative gamma prime, the gamma prime would be this subplot here, is kind of fellow travels this word W. And the way we say fellow travels, it says that there's two finite words A and B with bounded length, uniformly bounded length, which are A and B, which bring W into this gamma prime. So this is some notion of saying that basically this element, this path kind of contains W. And then we say that graph structure is growth quasi-tight relatively to H. H is a subgroup of G. Whenever you take a word W in H, the set of paths which avoid this W in this weak sense has zero density. So this is slightly complicated, but tells you that this YWC are the set of paths which do not contain W essentially. And basically, almost all paths eventually contain W. This is the notion. So intuitively, generic paths fellow travel W, but not in the graph. In the graph, it would be very, very strong condition, but in the group, it's enough to assume it's fellow travel in the group. And in particular, well, this might be slightly complicated as a condition, but well, a very simple case where it holds is where there's only one basically non-trivial component in your graph. So for instance, one non-trivial means that a component which contains at least one loop. So for instance, in this case, basically you have a subgraph which is this one, which is irreducible, and this is the unique irreducible component, and then you just have finitely many things which go into that. And this would be one example of such a thing. And counterexamples of such condition would
Sorry, yes, when you talk about that, what is H?
So, well, you could take H equals G in this case. This doesn't, in this case. Yeah, so of course you can say H equals G, that would be the strongest condition, which is true in many cases. But in fact, in some other cases, you need a sub. So you see, H could be a much smaller subgroup, a priori. So you might need this fact that these words are, appear all over the place, but possibly for a much smaller subgroup. That's the idea.
So I'm sorry, so
Yes.
non-trivial component means strongly connected component?
That's right.
And then you take H to be like generated by paths.
That's right. That's right. That's right. So if you have only one non-trivial component, then you can take H equals G, and that's kind of a nice case.
So is a trivial case of this that a generic word has an X in it? Is the-
Trivial word? Sorry?
A generic word in the free group contains the letter X.
The letter A.
Or A, sorry.
Right. Well, but you see, this is containing in this kind of weak sense. So you're allowed a prefix and a suffix. So sometimes you could...
And gamma prime can be as short as you want.
Yeah, well, it cannot be that much shorter because it's more or less the length of W, right? Because A and B have finite length, have uniformly bounded length.
Compared to gamma, it could be very small.
Yeah, gamma prime could be much smaller than gamma. That's exactly right. That's exactly right. Okay, so anyways, the thing is when you have a product of two groups, then basically, and one group has the same, and one subgroup has the same growth as the whole group, then this condition will not be satisfied. That's a point basically, because because basically words in that you can avoid. Yeah, you cannot avoid words in that. So, anyways, let's keep going. Once you digest this, then this is the general theorem, the most general theorem. Then we'll see application. So you have any almost semi-simple graph structure for G.
So it doesn't need to be automatically...
No, it doesn't have to be geodesic.
No,
No,
just whatever.
that's right. And in fact, the only condition is that there is a non-elementary subgroup. So H is a subgroup of G. And this subgroup could be much smaller than G potentially. But it has to have this nice dynamical condition that basically words in H kind of appear all over and over in this graph structure. So you don't even need that it surjects, but somehow the fact that it's non-elementary, this kind of saves the day. And once you have these loxodromic elements are generic, and in fact we can prove even more. We can prove exactly what we did with just bar, actually, that the translation length of elements grows linearly. So basically, there's some L, depending on the action, such that if you count the number of elements of length n in this graph, with translation length at least n times L, this is full density. So of course, the second one implies the first one because L is positive. So if tau G is bigger than n times L, it's bigger than 0. But this is kind of uniform. Also, there's other things you can say, which they're kind of a priori unrelated, but with the same techniques. Something which seems obvious, but I don't think it's obvious, that if you have a subgroup of infinite index in H, and well, let's assume that this structure is injective. So every group element is at most one representative. Then the number of elements of length n in this subgroup tends to 0 as n goes to infinity. Of course, if H has finite index, then you would expect there to be a positive proportion of elements which lie in this subgroup. And if H is infinite index, you would most definitely hope that the number of elements which are in the subgroups, they are actually 0 density. But this is not so obvious, because H could be like weirdly distorted inside G. So there are crazy possible Cauchy examples, but in this setup it doesn't have. In fact, this theorem is already interesting for hyperbolic groups. It appears in this paper of Guzel, Mateus, and Lacourant, and basically we can extend that. Once you have these ingredients up there, we can extend the proof. Any questions? Okay, so I guess I have 10 more minutes or something, or maybe 15. 15? Okay, very good. Okay, so let me say what are the two main applications for this. So the two applications. So the first one is for relatively hyperbolic groups. So if you have a relatively hyperbolic group, you need two conditions to do counting. Suppose you want to do counting in balls. You need two conditions. The first one is that the parabolic subgroups, so this is relatively hyperbolic with respect to some family of subgroups, which we call parabolic subgroups. So suppose, for instance, that parabolic subgroups have nice geodesic structures. So for instance, if they're virtually abelian, this is enough. And second is you need some dynamic condition. And in this case, you can rephrase it in this way. So remember this growth quasi-tightness. In this case, you can consider the boundary of G, the Bodish boundary of G, and this boundary comes equipped with a Patterson-Sullivan type measure, actually. And you can ask whether the action of G on this double boundary is ergodic. In fact, it's known that for all hyperbolic groups, this is true. And there's even a recent paper on Butler and Fuhrman where they give a proof of this. But a priori, I don't think it's known in general for relatively hyperbolic groups. It might as well be true for all relatively hyperbolic groups. But in any case, once you have these two conditions, then you have any non-elementary actions of G on a delta hyperbolic space, again, you have genericity or loxodromic. In particular, a nice class that we probably are interested in is basically geometrically finite climbing groups. They have a geometrically finite group of isometries of a good old hyperbolic space. Then you have for any action, no matter how complicated it is, as long as it's a non-elementary action, you have this genericity of this loxodromic. And in fact, let me just remark what's going on here. So in this case, you would know that parabolic subgroups, which are the good old parabolic subgroups, stabilizers of points at infinity, are virtually abelian, and so they have nice automatic structures. And then the other thing is that when you have a group which acts geometrically finitely on, say, a cat -1 space, then the action is known to be ergodic. So here you need some dynamical condition. Basically, this is the fact that you need this condition. I mean, you can prove this condition if you have some geodesic flow on X, basically, on G, actually. So if G is a group of isometries of Hn, you have nice geodesic flow, you can apply, say, the Hopf argument, and you get this ergodicity. And in general, maybe you can do it, but somehow there's some technical issue. Any other question? Okay, and the other case, which I kind of wanted, which is somehow even nicer in a way, is for right-angle Artin groups. So in general, or Coxeter groups. So in general, can remind you the definition, you have just a graph. So you just have a finite graph, and you impose a relation, right? So you have a lambda finite graph, and you impose a relation. Let's say this is your lambda, and you impose a relation that element. So you have a generator for each group element, for each vertex. Sorry, let's call these generators A, B, and C for a reason that will become apparent next. And what we do is you define this group by saying that two vertex commute if there is an edge. So in this case, A and C would commute, but A and B would not commute, and B and C would not commute. So of course, so this is kind of a nice family of groups which kind of interpolates between free groups, which is what you would get if you get just a totally disconnected set of points, or an abelian group if you just get the clique graph. And in other cases, you get some intermediate case. So for people who are just slightly less expert on such groups, what group would you get in this case?
Z2 free product Z.
So I see, right? So this one would be Z2, and this now commute with this one, so it would be free product in Z2 and Z, sure. And you get a whole bunch of things like this. And also, the question is, again, if you want to do counting, remember that you want to avoid the case where you have a where you have a direct product. And it's kind of cool that for RAAGS, you can really tell very easily whether they're products or not, at least there's a simple criterion for which there would be products of smaller RAAGS. So if you take the opposite graph, so instead of taking this graph, you take the graph where there is an edge if and only if there was not an edge. So here you would connect this two and this two. And it turns out that it's very easy to see that, you know, if the opposite graph is disconnected, means that you can write this group as a direct product of smaller RAAGs. I mean, this is very, very well known. I mean, basically, look at us. Lambda opposite has two subgroups, two graphs, lambda 1 and lambda 2. Then, of course, this means that in lambda you would have a join of lambda 1 opposite and lambda 2 opposite, and you would have a join in all possible ways. And so this would be a free product. Sorry, this would be a direct product. So, of course, we want to exclude this case. And what's kind of cool, though, in this is the only thing you need. So for RAAGS, you get this application, and in fact, it holds for ArtinCoxeter groups and more generally, but anyways. What you could get is that as long as this group is not virtually cyclic, so you want it to have exponential growth, so for instance, and in fact, it's enough that it's not virtually cyclic, and it's not trivially a product. So basically, the opposite graph is connected, then we're good to go. So basically then if you take the set of vertex generators, and then you take any, so vertex generators are just these generators which are given by vertices, so sort of the canonical set of generators. Then you take any action of G on any separable hyperbolic space, and you still have the same properties. You still have loxodromics which are generic, you still have that the translation length grows linearly, and so forth. And yeah, you have that the infinite index subgroups have zero density, also all the nice properties. So in a way, this kind of closes the picture for these groups, because either they're products of, and in this product case, you can tell if one of those products have the same growth as the big group, then you cannot possibly have genericity loxodromic. Or it's not a product. And if it's not a product, you have all these nice properties. So I think this is kind of neat. So, so what I wanted to tell you, maybe, in the so yeah, so perhaps perhaps I will show you what are the ingredients of the proof in these two different cases. In particular for RAAGS. For RAAGS, it's kind of fun actually, because you can. Oh, in fact, another thing you get out of this analysis is that RAAGS have what I call exact exponential growth. So basically, this maybe is known, but I could not find it in the literature. Is that in fact, if you count just the number of elements in the sphere without caring about loxodromics or anything else, they just have pure exponential growth. But if you take the number of elements in the sphere, you divide by lambda to the n. This actually converges to a number. So this follows from the fact that they do have a nice graph structure, except yeah. So basically, there's an old paper of Hermila and Mayer where they do find a graph which parameterizes geodesics in this right-angle Artin group. However, that graph doesn't quite work exactly for us because it's harder to check whether this graph has this growth quasi-tightness property. So in fact, what we do is in the case where the opposite graph is connected, then this graph will have a unique recurrent component, just like in this case. So we have to modify this graph, but we can do it, and you get the graph which has all the unique recurrent component, and then you can apply all the story. And yeah, so yeah, I kind of wanted to show you how to construct this graph, but I'm not sure if I have enough time. So I don't know, maybe I can do it very quickly with a simple graph like this one. So yeah, so how do we do it? So it's kind of cool. So basically, what you can do is the following: you introduce an ordering. So this is the computational part. You can introduce an ordering of the vertices. Say A is less than B is less than C, and you introduce it so that A and B are not adjacent. You can always choose this, otherwise you're in a trivial case. And then you construct sequences of words. And sequences of words have this property that you pick I and J, which are not adjacent, and I is bigger than J. So here, what possibilities you have? Well, you can have C and B as a starting point, or you can have B and A, but you cannot have C and A because C and A are adjacent. And then what you can do is you can take all possible ways of extending this sequence in a monotone way, but in a way that, well, yeah, you have this last condition here, which is whenever you have an element which is not bigger than the first element, it has to be not adjacent to at least one of the previous ones. But anyways, here you can tell what the possible choices are. So basically, you can expand. You can keep going from this. You can expand the sequence to, you can do BA-BC or BAC. And in this case, you can do CB or C. So you get this finite sequence of words which are naturally organized in trees. And then you can construct a graph out of these trees. So let me say how to do it. So basically you put these trees, they have C, B, C, and you have B, A, C, and B, A, B, C. And then you connect these trees. And the way you connect these trees is the following, that whenever you have, well, first of all, you cut the head of the tree. So basically, these elements, you kind of forget them. And then what you do is, whenever you have a pair of elements which are not adjacent and they're decreasing, you connect the I vertex, every I vertex with the J vertex of the ij tree. So let me see what's going on. So for instance, if you have C and B, which is such a pair, so you connect every C vertex that you have, you connect it to the B vertex in the CB tree. So basically you connect this here, and this here. And then exercise for the audience, what is the other pair? The other pair is B and A. So you have to connect every B vertex with the A vertex of the BA tree. So you have one which goes like this, and one which goes like this. Okay?
You don't use the top one because you...
No, this one you forgot them. You record, these are the heads of the trees, which kind of tell you which tree you're looking at. But they're not going to be part of the final graph. And so this is the main part of the graph. And then you just add one thing. So you look at this BA tree. So this contains A, B, C in the usual order. So you just take you take an initial vertex, let's say the 0, and you connect them to all of them, to A, to B, A, to C. And I claim that this is the final realization of a graph which represents geodesics, not quite in the Artin group, but in the Coxeter group. So where every element has order 2. And yeah, so in fact, the way you read things is that you read elements by looking at the endpoint of the graph. So for instance, you go from this to C if you read C, you go from this to this if you read B, you go from this to this if you read A, and so forth. And then you have a graph, and this graph is strongly reducible. It has only one non-trivial component. And in fact, you can modify this to get the Artin group by you kind of double each vertex. Because basically what you can do here, instead of doing, you have a path, is a path of vertices, but in the Artin group you can do, say, A 10 times instead of only one time. So you introduce basically a loop around A which says I can do A many times, or I can do A inverse many times. So there's a canonical way to go from this to that. Anyways, and then you get this nice matrix, and you can compute, for instance, the growth. And so let me just finish with this example that I computed during the night when I couldn't sleep because of the jet lag, is that in this case, you get all these admissible pairs, and you have this 6 by 6 matrix, and you get, so for the Coxeter group, you get this number as the growth, so it's the square of the golden mean, basically. And then for the right-angled Artin group, you get 12 by 12 matrix, and you can compute this, and you get 4.2. And it's reassuring because the free group on 2 generators has growth 3, and the free group on 3 generators has growth 5. So this element, this number is between 3 and 5, which I think is good. So I think I'll stop here. Thank you.
Are there questions for Giulio?
Do you want to say a little bit about that technical point of completing the non-compact boundary?
Oh yeah, that's for you. That's right. So this is very, very dynamic. In fact, I have on slide. So basically, the point is that so the whole point is that you don't know whether there exists a stationary measure on this boundary. And stationary measure for this random walk. Basically, you push this measure and you take the average of all these push forwards. And the reason is because of compactness. So you have this huge boundary, which is basically the Horner function boundary. So basically, you can embed x in the space of continuous functions on x, which vanish at some point. And then you take the closure of x in this huge compact set. It turns out to be compact because everything is bounded pointwise. However, this is a compact set. So it's always compact and traceable, but the topology is kind of weird. It's a very weak topology because basically it comes from Tikhonov's theorem. So everything converges here, but so you do get a stationary measure here, but you can't quite use it yet. And then what it turns out is that you can map the Horner function boundary into the good old Gromov boundary. And the reason is basically you have a Horner function, and basically this Horner function has a point of minimum. And this minimum is either inside of x or it's on the boundary. So there's a very general procedure using metric spaces which gets you here. So the whole point is that eventually you have a stationary measure on this space which is compact but with a weird topology, and then you have this, you push it forward to a measure which is on this space, which is non-compact, but it's the topology you want. And then you use the usual arguments of Furstenberg, Margulis, this kind of arguments to extract, for instance, convergence to the boundary of this. It's the same as for Lie groups.
What happens for geometrically infinite claim?
I don't know. Somehow I haven't thought about this. The reason the thing is, I mean, these theorems are pretty general. The thing is, the problem is that then you have this bunch of conditions and you want to have theorems which you can apply them to, and so it so happens that you can get it in that case. But so I don't really have too much of an intuition on that. Of course, it's a good question.
Oh, well, let's thank Giulio again.